Our
Come
next
on.
speaker is Robert Avram. Robert is a software engineer currently working at Reve Digital at Cologne and spends a lot of his time writing microservices in Clojure and Scala. His talk is, does functional programming actually help in production? So please, a warm welcome and a big round of applause for Robert.
Right. Hello. I do have to say this is a bloody big hall. I think it's the biggest hall I've ever spoke in. So thank you for having me. Thank you for coming to my talk. My name is Robert Avram. I've been told today that I'm a software commodity, and I work for these people. Now, I do like working for these people out of two reasons. The first one is that, well, they pay me, so I get to live, which is nice. But the second one is, and of course more important, I get to use excessive amounts of these in my day-to-day job. Now, I do have to still use some of these, but the first ones eclipse the second ones by a large margin. Now, these two things are two programming languages. They're Clojure and Scala, two functional programming languages. How many of you have heard of them? A lot of you. How many of you use them, either of them? Some of you. Brilliant. Now, this means that I get to do a lot of functional programming every day, and I get to use it in a big ecosystem-y, ever-changing, complex, every buzzword you can think about environment. And it's quite fun simply because at such a large scale, you sort of see exactly what you can squeeze out of a paradigm in order to help you. And basically, that's why I'm here. Now, first things first, what is functional programming? How many of you do functional programming? Okay, a lot of you. How many of you have read functional JavaScript or functional programming in Java? Okay, that's good. So this thing is basically a programming paradigm, and it's a fairly odd one because it just simply enforces a discipline. And the discipline is you should program with functions, hence the name. But it also says that these functions have to satisfy three rules. The first one is totality, determinism, and purity. And if you build a program where all of the functions satisfy all of these three rules, then your program gains some interesting properties. Now, the question is, what can functional programming promise? Can it make application improvements? Can it make it faster? Can it make it better? Can it make it less error-prone? Now, the answer to all of these questions is generally no. Like with any other paradigm, this solely depends on how you implement your application. But can functional programming improve the way that we as developers sort of build an application? And the answer to this question is probably. And I'm here to argue this probably. Now, what I'd like to do is I'd like to talk about properties that we value of code bases, things that we talk about very often amongst each other, things that we value, but we don't know exactly how to achieve because they're fairly difficult to achieve. And these are a number of ITs. I've picked 5 of them. There's modularity, there's testability, composability, concurrency, IT, and manipulability. And what I'd like to do is I'd like to go through each one of them and show you, hopefully, how functional programming might aid their achievement. So it's not going to guarantee them, but hopefully aid their achievement in the process. Now, modularity, what do I mean by this? What I mean is how we semantically structure our code, how we put pieces of code together in sort of structures in packages, files, objects, modules all together in order to achieve some properties. Now, the two most common properties that we want to achieve by doing so are isolation and searchability. Isolation is sort of driven by separation of concerns. We put code with the same concern together because if it's in the same context or domain, I can understand it better. But this has an immediate consequence, namely if I want to search for something that is from that domain, I know where to look for it. Now, these two are fairly difficult to achieve, and there's a lot of people in this world that had opinions about them, they wrote books about them, and they sort of led to programming patterns that more or less work. And 2 of these patterns are the service layer pattern, repository pattern, amongst a bunch of others. How many of you have heard of these patterns? Okay. So I'd like to basically go through them and see exactly what they do. So the service layer pattern and repository patterns are a way to semantically separate code. Service layers typically do or contain business logic, and repositories contain low-level effects, generally related to information retrieval and information storage. And the way we build them is by means of a combination of 2 things. On the one hand, dependency injection, on the other, object composition. So what tends to happen is that these things tend to be objects, and they receive other objects as dependencies, other repositories or services. that feed into the methods of these objects, and the methods use them in order to implement whatever they need to implement. And these sort of satisfy or create these two properties. I have now two isolated pieces of code. I can search for them because I know where they are, and I can understand them individually. But by doing so, you create two problems. The first one is that it could very well be that methods in these objects don't use all dependencies, but you've parameterized the whole entire module. The second problem is that these methods are encapsulated. You've put a barrage of things in front of them, and that limits your access to them. In order to get to these, you have to go through this and this. Now, if you would like or would want to debug one of these methods, what would you need to do? Well, you would probably need to instantiate or inject all of the dependencies. You would probably, depending if you use a framework or not, spin up an application because it needs loads of configuration. You would need to orchestrate a scenario where this method gets called. You would need to start a debugger, and you would need to click yourself into oblivion until you actually find the thing that you want to find. So there's a lot of things that I have to do just to look at one method. So can functional programming improve this? And I think it can. Simply because in general, functional programs tend to be very static. Because of the discipline that we follow, functions tend to be very stateless. They don't influence the world that much. They're pure. We also use immutable data, which means that we have a lot of invariance and a lot of determinism, which means that functions can be open and accessible. I can make them static. I can call them from anywhere. Now, you can still clump functions together into service functions or repository functions, but instead of putting them, encapsulating them away in objects, you can just put them in a namespace, which is just a prefix for that function. So let's look at our example, right? How would this look like in a functional setting? So you throw away the entire object and you just have a namespace. It's just like a prefix for your functions. And this thing contains only the functions that it needs to have. And the functions themselves receive the dependencies that they need in order to do whatever they need to do. And they're open and I can access them from anywhere and call them from anywhere. So how would you debug this? You would look at a function, you would just write a main anywhere, prepare some data, and call the function and see what happens. Now this is dumb, isn't it? But dumb is simple and dumb is quick. And if you have thousands upon thousands of lines of code and about 19 services to take care of, you need dumb and simple in order to get your things done. You don't need orchestrated and architected in order to fix problems, because that will just make your program in anger. Now, testability. This sort of is related to what I've said before, namely structure influences both debuggability, modularity, and testability. If we look at our previous example, how would you test one of the methods in this? Well, probably in the same vein as you would debug it, right? You would need to inject or selectively mock all dependencies. You would probably need to start up a fake application, depending on what you use. You would need to orchestrate a scenario again, and then call the function and see what happens. Now, how would you test this in a more functional setting? Well, you would prepare some data, and you would call the function. Well, almost I lied. That's not actually true. That's simply because functions are complicated, right? Functions don't do just simple things. They do side effects. They influence the world. They change what is around us. But functional programming has an answer for this thing as well. Namely, the discipline also forces you to split the functions that you have. And it forces you to split them into pure functions that only do data transformations and side-effecting functions that actually do I/O. Now, if you apply this, you'll also notice that you start testing in a separate manner. You'll start testing your pure code in one way and your side-effecting code in another. And if you continue doing this, you'll all of a sudden realize that your pure function must be as logically dense as possible, simply because you want to test them on a data level. And this basically becomes what I said before: prepare some data, call the function, see what happens. And in this case, you would probably do some property-based testing because this becomes more accurate. Your side-effecting functions will become extremely dumb and extremely simple, probably also extremely many because they're as simple and as dumb, but they should do one thing. You write a database, you read from a database, but you don't do more than that. And you would tend to want to test them integratively. So you won't want to mock anything because you want to test the side effects. So if you want to write a database, you're going to spin up a database, write a database, and see what happens. Now, in our Clojure project, this is so ingrained in our architecture that we have separate packages for each one of them. So if you take a look, we have two resource folders, source folders, one source and one source int. Source is for data transformation, source int is for our side effecting transformation. In the same vein, we have a test and a test in, so we test them separately as well. Now, the upside to this is that your tests become accurate and localized. You test separately and you concretely concentrate on whatever that thing is doing, and you're trying to gain as much as you want out of it. The downside is that you're probably going to write a load of tests, additional tests, just because you've separated them. Now, every time I tell people about this, the argument that they yell back at me is, well, in programming, functions are not the sum of their parts, right? If I have functions that I use in my implementation, if they work, doesn't mean that my implementation works. And the answer is probably true. Functional programming doesn't simplify testing. Complicated code will remain complicated, and the way you test it solely depends on you. But what I can guarantee is that doing this will remove some worry about the constituent parts of your program. And if you try to test something complicated, where you know that the constituent parts will behave exactly as you expect, it's much simpler than trying to test it full on. Next thing I would like to talk about is composability. Now, this sort of implies a bit of reuse, right? If I write some piece of code that I compose into another part of my program, I can reuse it there. And in standard object-oriented fashion, this comes in the form of object composition. How many of you know of object composition? Okay. Actually, all of you should know of it because I've shown an example of it. So this thing is built with object composition. Basically, you have an object and you compose other objects into it, basically as dependencies, and it receives these objects and uses them in order to implement them. Now, in functional programming, this comes in the form of function composition. And basically means that if I have a function that takes an int and spits out a string, and I have another function that takes a string and spits out a byte, because the output of one function is the input of the other, I can put them together, and I get a third function that does both at the same time. Now, one interesting thing that functional programming has, another type of composition that no other paradigm has, is effect composition or side effect composition. You can make side effects compose together. And the most compelling example of this that we also use almost everywhere is that you can make errors compose, or computation that returns errors or throws errors compose with each other. So let me give you an example. Imagine you have a user job, you have a batch job, you compute for every user in your system. And this thing has to do a lot of things, right? It has to talk to a database to get some data, it has to talk to some services to get some data, and uses this data to compute some data out, right? Now, because each one of these calls go outside of your system, they most probably can fail. What you actually like to do, however, is if one of these fails, you wouldn't like to fail the entire batch job. You would like to skip it, log something, and then continue, right? So how would you go about solving this problem? One way would be to handle each and one of these calls. The problem with this is that you have to find a way to then break out of the execution, but continue with your batch job. And this also sort of pollutes your logic with error handling. Another way would be to keep your logic clean and do a try-catch at the end, right? But again, you would still have to find a way to go back, skip this execution, but don't kill the entire batch job. And second of all, if you push try-catches away, at some point you have to do them. And they might reach a part of your program that doesn't really make sense because it's not related to the batch job at all. How do you solve this problem? One way of solving it is by making errors compose. And the way you do this is by defining errors as a data structure, or computation that can return error as a data structure. And your functions, instead of throwing errors, would return this data structure. Now, the way you do this is by making a small observation about how computation works. Every piece of computation can have one of two outcomes. The first one is a success, whereby you get the result of your computation. And the second one is a failure, wherein you get the error of your computation. It might be a stack trace, a string, whatever you want to define as an error, right? So any piece of computation is actually a disjunction. It can either be one or the other, more or less like Schrödinger's cat. Now, ironically, you can actually encode this into code. And I've picked Java as an example because I think most of us understand Java. And this is represented through an interface called either. How many of you have heard of either? Okay, some of you. So either is basically a type, an interface that has two type parameters. On the one hand, it's the type of your error, the one that you want to throw. Could be a stack trace, could be a string, whatever you want. And the other one is the result type of your computation. And this thing has two instances. The first one is a success. And this instance only contains the result of your computation. The other one is a failure, and this thing only contains the error of your computation. Now, the way you use this is that if you have a function that will throw errors, you use this type to represent the fact that it might return two things. You say, my getUser function might either return some sort of throwable object or it could return a user. Now, in Java and languages that don't have this built in, you have to do the side effect. But after you've done it, you basically just instantiate one of these two classes. If it's a success, you say success of the outcome. If it's an error, you say failure of the exception. And now these two things are data. Now, the brilliant part about this is that they now compose. So if you have a function from int to either of error to string, and a function from string to either error to byte, you can put them together to get a function that does both of them at the same time and returns either of error or of byte. Now, the brilliant thing about this, and it's due to the semantics of this data structure, if the first one fails, the second one never executes, simply because you're in the failure branch and it doesn't have anything to feed the second computation that you've composed it in. So you have basically like a built-in circuit breaker. So let's look at our previous example. If each one of these calls would return an either, I could compose them together. Now my logic would be a bit polluted by this data structure, but because it's data, it sort of still remains a bit clean because it's data that I return. If one of these things fails, then the whole execution stops and I get a failed. But I can filter this failed out of the batch job later on, so I can basically, I don't kill the entire batch job. And I can handle this either whenever I want. And plus, I can also compose other computation that happens later on within this data structure. So I can basically merge it with my entire program. Now, the next thing that I'd like to briefly talk about is concurrency. And I'd like to talk about concurrency simply because it's sort of conflated with functional programming. People tend to say that with functional programming, concurrency sort of goes away. But I'd like to tell you that it isn't going away. Functional programming is sort of good at some problems of concurrency, but some of them remain the same. And what it's good at is three classes of problems. It's good at concurrent reads, at data distribution, and at composition of concurrent tasks. Now, concurrent reads simply is due to mutable data. If I have mutable data, any thread can read it, and if they try to change it, they get a copy. So that's fine. Data distribution is sort of like the inverse of this. Because I have immutable data, I can distribute it on any node I want, and it basically is never going to change. They get copies of it. Now, the last one is actually quite interesting. In functional programming, concurrency is a side effect. And much like the either data structure before, it's represented with a data structure. And because it's like a facade for concurrent tasks, I can compose other concurrent tasks into it. And the ironic thing is that you actually know what it is. It's the humble future of promise. How many of you use future and promises? Okay, if you use JavaScript, this is basically everywhere in your code. Now, future and promises come from functional programming, and they're just a representation of something happening concurrently. And much like the either data structure, they compose. In JavaScript, the composition primitive is then. Now, the brilliant part of this is that even though they compose, each one executes concurrently, there's a guarantee that is set, namely the callback that you give this future, the transformation that happens at the end, is guaranteed to execute sequentially and once all the futures complete. And it's guaranteed to also execute when all of them successfully complete. So what's this good for? Well, it's good for if you have something like this. If you have a function that calls a number of services and returns some data and needs the data to compute something, this is what functional programming is good at. If you make each and every one of these calls a promise or a future, it will work exactly as you might expect. But for problems where you have some inherent common mutable state, imagine you have like a chat application where you have like an observable of some kind that you have to manage, like a session of some kind, then this doesn't really work. There's nothing in functional programming that can help you with this problem. You have to use standard solution for this method, like software transactional memory or semaphores or what have you. Now, there are functional languages that built these features inside. Clojure has this, but there's nothing inherent functional about these things. They're just standard solutions. And the last thing that I'd like to talk about, and then I'll leave you alone, is manipulability. What do I mean by this? Is the way we program with data. Now, most of programming that we do just involves transforming data, right? What are HTTP requests? They are bundles of fields and values. They're lists of hash maps. What are classes and data classes? Well, they're fields and values. They're hash maps. What do I do when I validate a request or a class? Well, I have an operation or data structure. What happens when I transform a request or a class? Well, I have another operation or a data structure. Most of programming involves using data and either associative or accumulative data structures, namely hash maps, dictionaries, sets, vectors, what have you, and transforming these into something else. And this is basically the computational model of functional programming. Everything you do in functional programming is apply functions to data, apply functions to data. And this is so ingrained in the paradigm itself that it developed abstractions, mathematically proven abstractions for operation on data. And you can sort of clump them into three types. You have transformations between data structures, which are called endomorphisms. You have transformations from a data structure to a value, which are called catamorphisms. And you have transformations from a value to a data structure, which are called anamorphisms. Now, ironically, you've probably used them. If you use Java streams, things like map, flat map, filter, collect, these are all endomorphisms. If you use things like reduce, find, first, for each, these are catamorphisms. The same goes for JavaScript and a lot of other languages, and all of these come from functional programming. Now, how many of you do Java? Some of you. How many of you transform lists using the stream API simply because it's more convenient? Okay, most of you. So this isn't really that far-fetched, right? It's quite useful. Now, functional programming languages are rich in data and data structures, and are richer in the operations that they provide for transforming data and data structures. So if you truly do programming with a lot of data transformations, I'm not talking about big data, but general, just programming, like just move data about, then a functional language will most probably help you more than any language would. Now, as I've said, I'll leave you alone after this. What's the conclusion to my talk? Which is apparently shorter than I expected. Functional programming is not groundbreakingly complicated. The deeper you go in the paradigm, it does get complicated, but I don't have to go deep in order to use some of its novelties to my own benefit. What I can guarantee you is that things won't change that dramatically. You'll still think about problems the same, you'll still approach problems the same way, but in time you'll notice that some things will change. Simply because it circumvents some problems that you used to think about before. So if you wanted to isolate, debug something, this is already there. Compound error handling and error composition already have it, concurrent calls, and a bunch of other things. And one of the most interesting things that happened, which I've noticed throughout time, is that it sort of absorbs subtle worries that we have about code and data, and in particular worries that we have about time. Because we use immutability and because we use a lot of data transformations, once I've defined something, it's going to stay that way throughout the lifetime of my program. So I don't have to think later on what happens if I do this here. Would it influence something that I've done 2 days ago? So generally, functional programming programs have a higher degree of invariance than other programs. And invariance is good in big systems because you won't get errors where something that used to behave some way before behaves today differently. Now, I do thank you for your patience. I do thank you for your presence. And if you have any questions, feel free to ask them. Thank you.
We have time for questions, all right? Here. Ready?
Hey.
Hi.
So can you tell me one type of problems that the functional programming way is bad at?
For one type of problem?
Problems, yeah. Like, most of the times when somebody have a lecture for functional programming, it's always like, this is better, this is better, this is like kind of the same, but never this is bad.
So I thought one example, and this I've had to implement this summer, is exactly this. If I can go back to it. Generally, when it comes to things like these, you have to do a lot of calls everywhere just to gather information and then transform that piece of information to something else. The abstractions and the things that functional programming gives you allow you to do this in a fairly compositional manner. And that means that your code tends to look very much as if you were doing it locally without any side effects at all. So talking to a database, you don't have to think about, oh, does it throw an error? Oh, does it talk concurrently? Oh, does it do this and that? Generally, you have something like an either or like a future, or there's other things for these things that where you pretend this thing is happening and you compose it with other things and it basically looks normal. You just say, oh, it talks to the database, I might receive an answer. Talks to the service, I will receive an answer. And if one of these fails, then it's guaranteed that the whole execution sort of will stop. And you get some valid answer at the end that you can sort of interpret. But when you implement this, you don't have to worry about any of that because this is sort of taken care of for you. So these are types of problems where functional programming is good at. If you want more, then talk to me after this talk. I have a bunch of examples. Any other questions?
Right.
More question.
Yeah. Hey, and thanks for the great talk. My question is, from your experience, what kind of use case would you not use functional programming for?
Game development.
Sorry?
Game development.
Okay, fair enough.
Or systems programming, because there's no proper functional systems programming languages as of yet. Rust is somewhat ideal, but it's not as functional as you might expect.
More questions?
Yes.
Hi. Do you think that functional programming proving has place in production?
You mean theorem proving? Or what?
Yes, like proving that the program works in a functional way.
Well, that depends on what you mean by production, or how you define production. For a web application of some kind.
Maybe, for example, a backend service or a desktop application.
Less. So the guarantees that the paradigm provides as a whole, I think, are sufficient for that. Domains where proving might be helpful are things like, I don't know, think of NASA, where you sort of need to know exactly that the program works exactly as it should work, otherwise you lose billions of money. That's where probably theorem proving would work, and also things like fraud detection, where you have a bunch of sensitive information, but a back-end system, I don't think so. You could try it out. If you do it, I will be thoroughly impressed. But I don't think it's really necessary in general production system.
Right. More questions? Come on. We have time. You just have to raise your hand.
You still have 13 minutes. That's as far as I can tell. So. If not, then
Perhaps while we are thinking about your question, I will ask a question.
ask really.
You mentioned you're using Clojure and Scala.
Yeah.
For production apps. Why don't you go all the way and use Haskell, for example? Because Clojure and Scala, they have imperative escape hatches.
Well, I could give you the stakeholder answer and the developer answer. The stakeholder answer is because Haskell developers are fairly hard to find. And the developer answer is because Haskell is a bit complicated. It has it's not as complicated as you might think, but it has quite a learning curve. And ironically, we used to have a service written in Haskell. It just read Kafka and wrote to a database and was subtly deployed in our environment of about 150 microservices. Nobody noticed it because it just did its job. But one day, one of our architects saw it and he got a bit mad because if you want, in our case, to deploy some new service with a new language, you sort of have to go through the architecture board and tell them, I want this new language because I think it's pretty. And if they accept, you can use it. Otherwise, it doesn't. The thing is, the second or the third reason is because we have sort of like the JVM as our basis runtime, and a lot of our other services are built with Java. And we use a lot of libraries as a whole, which are Java libraries. And if you use Clojure and Scala, you can directly access them because they have full interoperability with Java. And it's sort of akin to our whole platform. But there has been thought about this in my team, and we tried at one point playing a bit with Frege, if you've heard about it, it's sort of like a Haskell port for the JVM, but it didn't satisfy our needs.
Thanks for the answer. More questions? Are there? Oh, yep, there are. There was a guy before you. There you go.
Yeah.
Thank you. I was curious, what kind of application are you writing on Clojure?
What do you mean exactly?
I mean, you have some some things, some project that you are using this. I mean, what is the real world case that you are using this Clojure on?
What's the real world case? So our service is basically the main service that handles orders. So what we do as a company is we have an online shop, an e-commerce platform where people can order their groceries and we ship to them. And our Clojure application is basically the order service that handles all the orders. It's fairly critical within this thing. And first of all, we chose Clojure. I wasn't there when they chose Clojure, but they chose Clojure because it's a simple, very terse, very powerful language. And a lot of its things, a lot of its features, both the immutability and the way this whole data transformation thing that I've talked about is very helpful. When you have a bunch of orders with a bunch of data that you need to sort of validate and transform and think about and map to something else and sort of put in other services and put in Kafka and whatnot. And it's very helpful for that particular reason. I don't know if that answered your question.
We have one more question here.
Yes.
Hi. So my question is, how do you decide when to use property-based testing?
Good question. That's generally, this is my opinion. It's not a team opinion, but it's the way I think about it. If I can think of a property for the thing that I've implemented, then I'm going to use property-based testing for it. If not, then I'd have to either think about it for longer, for which I don't have really that much time, or I just have to test it the normal way, unit test it or what have you. So there's no general rule when we use property-based testing, but the general idea is if you see a property or you feel like there's a property in this function that you've implemented, you should probably use for property-based testing for it. But we use property-based testing to test it. A derivative of what I've given this as an example. Any more questions?
Any more questions? Yep.
Yes.
Okay, I'm not sure that's a right question for you, but why Clojure and Scala and not Java, for example, with libraries for immutable objects or immutable data and streaming and so on and so on? I'm pretty sure that what you told us is some kind of idea that you can express on pretty much every language in 2019, more or less.
So to repeat the question, why Clojure and Scala, not Java, with some library that uses immutable data and transformation and so on and so forth? This is simply because these languages were built with these things inside of them, and they support them in a much natural and first-class fashion. I don't particularly like languages where you bolt on features on top of them simply because you can encode them in the language itself, but the language itself is not built for these features. There's good examples for this in Haskell. So even though you have libraries in Java for these, the language itself, both syntactically and semantically, was not built to support these things. And you notice when you use them that there's a lot of clutter, there's a lot of things, verbosity that you have to use just to get to the same thing. Whilst if you take Clojure or Scala as an example, you can express the same thing in much, much less code and a bit more concise and expressive. So yes, a solution to this, which also other people in our company do, is they take Java and say, I don't have any alternative, I'll take some library like Bava, I think it's called, and we'll try to use that. But you notice there's a noticeable difference between the same thing implemented with Java in a library and something implemented with Clojure and Scala. And I'll guarantee to you that the Scala version, if you can't understand Clojure, is much simpler to understand than the Java one. Any other questions?
Right. Any more questions?
Back there.
Up there. And I think this will be the last one.
So would you say that you use functional programming as a middle layer between your services just to map data from one service to the other?
Not really. We also have a lot of logic in between. So most of the things that we generally do is map data between services. If you have a microservice architecture, you realize at some point in time that everything you've learned at university is basically useless. Everything that you will do is map models to models because people are clever and think my model is better than yours. But we also do have logic, so there's much complex things that we also have to take care of, like making sure that the right amount of money gets paid and calculating things like, I don't know, differences between orders. And there's a lot of things that we also do in addition to just mapping data from one point to the other. And all of this is done with functional programming.
All right. Let's thank Robert again.